Assalamu alaikum and welcome to lecture number 6. In this lecture we are going to do some numerical examples on sampling and reconstruction. The next topic will be interpolation, and then we will conclude the lecture with the discrete time processing of continuous time signals. So starting from the previous lecture, this is the example I gave you as a homework, and I hope many of you have tried it. So in this example we are given the continuous time signal, and we are also given the sampling time, that is 1 over 6000. So in this example we are going to sample the signal and then we reconstruct it, right? So the signal is given, the given signal has these values. Okay, now the first thing is to sample the above signal. So to sample the above signal uh, using the equation this one, and all the values are given, so we obtain the discrete time signal, which is cos of 2 pi by 3 n. So let's first check the frequency of the discrete time signal. So comparing with the general form omega naught, here it will be equal to, because this is your discrete time signal frequency, so it is equal to 2 pi by 3. Let's check for the aliasing. So using the Nyquist condition or Nyquist criteria, sampling frequency must be equal to or greater than 2 times the highest frequency present in the signal. But in this particular signal we have it consists of only single frequency, which is 4000 pi t, right? So the sampling frequency can be found by using this equation, that is 2 pi by t. So we are given t as 1 by 6000, so that means the sampling frequency is 12,000 pi, and the highest frequency present in this signal is 4000, right? So that means the uh, comparing these values with this equation, so the Nyquist criteria is satisfied. So that means we are not facing the problem of the aliasing. So let's find the Fourier transform of the given signal. So this is the Fourier transform of the given signal. You know how you obtain this one, how you can obtain this one. So you just, because cos omega naught t, the original continuous time signal, is periodic signal, so we find the Fourier transform of the Fourier series of that, and from Fourier series we can find the Fourier transform. You know, we have done this, right? So this is what you get after the Fourier transform, right? So x as j omega equals to 1 by t, summation from minus infinity up to infinity, xc omega minus k omega s. So by putting the values in this equation we get this waveform, or this graph. I hope you can do it, right? So I want you to do it by yourself so that you know how we plot this signal. Again, the cutoff frequency of the low pass filter we are going to use is, because this problem consists of two parts. In part 1 you find the discrete version of this signal, and in part 2 you need to reconstruct this signal, right? So to reconstruct the signal, we first check whether the Nyquist criteria is satisfied or not. So we have done this already. Now we are given that the filter has cutoff frequency equal to omega s by 2. So omega s is 12,000, so that means 6000 pi, right, is your cutoff frequency of the low pass filter you are going to use. So this area shows the dashed lines, shows the spectrum of the low pass filter, right? So the cutoff frequency for the low pass filter is 6000 pi, and it has gain equal to t. So multiplying this with the original signal, we can reconstruct the signal. You understand, if you are given the Fourier transform of the signal and the uh, filter response or the system response, so just multiplying the filter response or the system response with the signal, you get the output, right? So the output is represented by x r j omega. So taking the inverse Fourier transform of x r j omega, right? So because if you multiply the two, you get two impulses, right? That is at 4000 pi and minus 4000 pi, and it is well within the range of the filter. Also the gain of the filter is t, so when you multiply the amplitudes with t, you get pi and minus pi, right, which are at 4000 pi and minus 4000 pi. So taking the inverse of this two pulses, which are 4000 and pi and minus 4000 pi, and amplitudes equal to pi, you get the cos 4000 pi t. Now if you look at this one, the reconstructed signal represented by xrt exactly equals to xct. So that means you can exactly recover the reconstruct the signal. Similarly, let's take another example. Here the continuous time signal is equal to cos of 16,000 pi t, and we are using the same sampling period. Okay, so the sample version of this signal will be equal to xn, and it is equal to xcnt, right? So putting value here of the sampling time, we get this, and by simplifying we get cos of 2 pi by 3n. So we get exactly the same expression as we had for the case when the input signal has frequency of 4000. Input signal was equal to cos of 4000 pi t, right? So although in time domain these two signals are different, but after sampling we get the same expression for both the signals. So let's check first whether there will be aliasing. So to see whether there will be aliasing, we'll check the condition of the Nyquist. So Nyquist says that omega s should be equal to or greater than 2 times omega naught, which is the highest frequency present in the signal. But in case of sinusoids, you understand the highest and the lowest, they are same, and it consists of only single frequency, which is omega naught. Now by putting values, we see that the sampling frequency comes to be 12,000 pi, whereas the signal frequency is 16,000 pi. So putting these values in this equation, so we see that the Nyquist conditions are not satisfied, so that means there will be aliasing, right? So in this case, again we use the same filter, that is the same low pass filter with cutoff frequencies equals to 6000 pi and gain equal to t, right? So we will get the output signal, which is equal to output or the reconstructed signal, that is equal to xrt cos of 4000 pi t. You understand how we get this one, right? You understand that the response is multiplied with the signal. So if we multiply this with this one, right, we get two pulses, that is 4000 pi and plus 4000 pi and minus 4000 pi, and because the gain of the filter is t, so this t cancels with this one, so you get two impulses at minus 4000 pi and 4000 pi. So if we convert this into time domain using the inverse Fourier transform, we get x reconstructed equal to cos of 4 pi t. Now if you compare with the original signal, x reconstructed is not equal to x of xct, and you understand why this is so. So you understand aliasing is a big problem, right? And due to aliasing, you cannot reconstruct the original signal. Now how we can avoid aliasing? So to look at into the aliasing, we see that aliasing occurs when sampling frequency uh, is less than 2 times the highest frequency present in the signal, and this causes severe distortion, and you cannot get the uh, reconstructed signal equal to the original signal. So to avoid aliasing, we can increase the sampling frequency, but there are some situations in which we cannot increase the sampling frequency. So if we cannot get the if we cannot increase the sampling frequency, we can use a pre-filter or a low pass filter before the sampling to limit the signal bandwidth to the required condition of the Nyquist, right? So you understand there are two ways we can avoid the aliasing. The first is that you increase the sampling frequency, right? And the second is, in case you cannot increase the sampling frequency, in that case you can decrease the bandwidth of the signal. To decrease the bandwidth of the signal, we can use a filter so that it filters out the higher frequency component, so that we can limit it to the desired range, so that we can avoid the aliasing. So this low pass filter is called anti-alias filter, or AAF, and it serves two purposes. First, it prevents the aliasing, and the second, it limits the signal bandwidth. Okay, so for example, in speech signal, in telephone quality signal, right, we have highest possible sampling frequency is 8 kilohertz, right? Let me write it. So for example, that's the original spectrum of the speech signal, your voice signal that you transmit on telephone lines. So in telephone lines, the maximum sampling frequency allowed is the linear, right? So f sampling is basically equal to 8 kilohertz, right? So that means the maximum voice frequency can be, right, because this is in linear, we can just compare it, that fs should be uh, according to Nyquist criteria, it must be, fs must be uh, equals to 2 times the, for example, we represent the highest frequency by omega n, sorry, not in fact just the linear frequency, right? So the linear frequency can be represented by f sp for speech signal, right? So because we are given that we have maximum frequency equal to 8 kilohertz, right? So 8 kilohertz, that means the f speech signal, right, f speech signal should be less than 2 times of this, or we can say that f speech. So that means f speech signal can have highest frequency, which is equal to 2, will be divided this side, right? So you get 4 kilohertz, right? Because in this particular example you cannot, because the systems are already there, so you cannot increase the sampling frequency. So what you will do, you will use the AAF, right, or the anti-alias filter. So what it will do, before sending the signal to the telephony, we'll have a low pass filter here, and what will be its maximum frequency, cutoff frequency. So because maximum can be 4 kilohertz, so for example we have this. Okay, so its not shape will not be like this, it will be something like, let me draw it. Right, so we'll use a low pass filter with a cutoff frequency of 4 kilohertz. So when I use a low pass filter for this signal, I will get this signal. Now in this signal you can see it meets the Nyquist criteria because it has maximum frequency of 4 kilohertz. So if I put 4 kilohertz here, so 2 4s are 8, so you see the Nyquist criteria is met and we avoid the aliasing effects. Okay, so this is the block diagram for the modified system. Here we have anti-alias filter, that is a low pass filter. So you have input speech that consists of so many frequencies, maybe up to 20 kilohertz or maybe more or less, right? But that's for sure that it's far greater than 4 kilohertz. So we will use a anti-alias filter, and anti-alias filter for this particular example will have the sampling frequency, the cutoff frequency that will be equal to 4 kilohertz, right? So 4 kilohertz and minus 4 kilohertz. So what will it do? It will just pass only these frequencies and it will cut the higher frequencies. Now you have analog to digital converter. Here you have sampling and all those things, so that will be fine. So I hope this gives you the idea. So instead of speech signal, we can have any generalized signal that has frequencies of this range. So you see we pre-filter it. So when we pre-filter it, so frequencies greater than omega by 2 are filtered. So you have this spectrum, right? So after sampling, you can see that these are not overlapped. Okay, although they are exactly equal to the sampling frequency, or these according to Nyquist criteria that we say that omega s should be equal to or greater than 2 times omega n, which is the highest frequency present in the signal. So here we are just equating it, right? So that's why you get this spectrum and you can easily reconstruct it using the low pass filter, right, with cutoff frequency equal to omega s by 2 and gain equal to t, right? So that's the parameters for the low pass filter which is used to reconstruct the signal, right? So then that's all for the anti-aliasing filter. Let's start the new topic, that is the reconstruction. So reconstruction is a process of converting from the discrete time into the continuous time, and the device that performs this operation is called digital to analog converter. You understand that many of the applications in the discrete time, basically they come from the continuous domain, right? So you understand why we do the processing in discrete domain, right, or in digital domain. You understand, I have, before starting this chapter, I have given you an example, and I hope that clears you understanding why we prefer digital signal processing, right? So after doing the processing, we need to convert the signal again to the analog, right? There's dozens of examples that you can think of, right? This easiest is the speech signal, and speech signal is generated by our tongue, right? And that's analog. So if the transmission system, for example the telephony system, is digital, then we have to digitize this signal. And at the receive end, again, because our ears respond only to the continuous time, right, or analog signal. So after transmission, we need to, at the receive end, we need to convert the signal back to the analog domain so that we can understand, right? So the first thing you have done for the how we can go for the discrete domain, you understand the sampling and those things. So now let's come to the second part where we are going to reconstruct the signal. That means we are just going from digital to analog again, right? So the xn is first converted into sampled continuous time signals, right? Then XST, which is the sample version, is passed through the reconstruction filter to produce the analog signal, and we represent this reproduced signal as in the previous examples, the XRT, the reconstructed R, right? And we check whether XRT is equal to XAT, the original analog signal. So we can, if the sampling frequency satisfies the Nyquist criteria, right? So the low pass filter we use has the frequency normally equal to sampling frequency by 2, that is 1/2 of the sampling frequency, and it has a gain equal to T, so that it can reverse the scaling things done while we are moving from continuous to discrete. So this is the again, if we talk about the ideal low reconstruction filter, so this is the ideal reconstruction filter, right? So you understand this is in the frequency domain, so in time domain it will be a sinc. That's based on the previous things you have done. Okay, so that's the block diagram for the digital to analog conversion or discrete to analog conversion. Because in digital, in the discrete domain, you have samples at integer values, but the samples has continuous values by themselves. If the samples also have the discrete values, then we call it a digital signal. So the frequency domain relationship for the reconstruction signal is that you have a reconstructed signal XR j omega equals to, or XR omega equals to XS omega times the reconstruction filter's response, or HR omega. Right? So from the previous examples, you know, if the Nyquist criteria is met, then the reconstructed signal equals to the original continuous time signal. But if the Nyquist criteria is not met, then you understand there will be aliasing and they will not be equal. So let's write some equation, right? So if this is your frequency domain equation, if I convert it back to the time domain, then XR omega will be XRT and XSJ omega will be X of T, and because in frequency domain we are multiplying, so in time domain they will be convolved, right? So let's put in the values. So that's the expression for the XST, the sample version of the continuous time signal. So that's this one. I hope you are familiar with this equation. Again, the convolution and HRT, right? So that means we can write, remove the bracket, and we can just write it like this, okay? So again, if you look at this one, you can say that because these are the scales, you understand, right? And these are the impulses, and these impulses are convolved with HRT. HRT is the impulse response of the reconstruction filter, normally a low pass filter. Okay, so you understand that because we are convolving with the impulse, so you understand impulse is convolution identity. That means if you convolve anything with the impulse, you get the same thing. If the impulse is scaled, that thing will be scaled. If impulse is shifted, this will be shifted. So I hope you understand how we got equation 11 from here, right? So this is called the reconstruction or interpolation, right? So depending upon the filter, there are several types of interpolation methods. So there are different methods of interpolation. We'll study some of them. The first one is the ideal interpolation. So this is the frequency response of the reconstruction filter with ideal frequency response, right? And its frequency, its cutoff frequency equals to omega denoted by omega c, and it's equal to omega s by 2, right? 1/2 of the sampling frequency. And if we take the Fourier inverse Fourier transform of this, we'll get a sinc function, right? So the impulse response of this filter represented by HRT equals to sine of omega ct or omega ct. So that means sinc functions, we can write it sinc omega ct by t. Now in this case, because we say cutoff frequency equals to omega s by 2, so replacing omega c by omega s by 2, we get sinc of omega st by 2, right? And because omega s equals to you understand this relation, you have done so many times, so that is omega s equals to 2 pi by, or in fact product of omega ts, right, which is the sampling interval or sampling time, omega s into ts equals to 2 pi. So that means omega s basically equals to 2 pi by, this is a general relation, I hope you have, you know it, right? So replacing the value for omega s by 2, we can say that this is equal to, because omega s is 2 pi by ts, so that 2 cancels with this one, so you get sinc of pi t by ts, right? So we have plotted the responses here. So plugging the values into equation 12, right? 12 into equation 11, which is this one, so we get xrt equals to summation n running from minus infinity up to infinity, x of n sinc of pi by ts t minus nts, right? So you understand, because it's a sinc function, so sinc function has highest values around its when it's independent variable. I'm talking about the generalized one, whether it's in time domain or in frequency domain. But if the independent variable equals to 0, in that case it has the highest value, and it has 0 crossing when it's independent variable, or in this particular case we'll say when t equals to m into ts. So when m equals to 1, it has 0 crossing here, m equals to 2, 3, 4, and minus 1, minus 2, and so on, right? So the reconstructed signal, replacing the values, we get x r mts, right? So we are replacing t by mts, right? So and this we can write it that this is equal to summation n running from minus infinity up to infinity x of n, and here hrt. So in hrt we replace the t by mts, right? So from the previous slide you understand this is value, this one, right? So maybe you go back, if you are confused you can go back to the previous slide, and there you look at for the expression of reconstructed signal. Okay, so we can write it like this, and then we can take ts as common, so we get this expression. So that means now if m minus ts right, so if m minus n is 1, if m equals to n, in that case we get 1 for this, right? Otherwise, if they are not equal, in that case we get some integer multiple of ts. So in that case, because if you look at this equation, I hope you have the idea of sinc function, so it will result into 0, right? So drawbacks of this one, although ideal interpolation method gives the exact reconstruction of the signal from its samples, if they are right in all the conditions, it's important that they are satisfying the Nyquist criteria, and if they are satisfying the Nyquist criteria, then there will be no aliasing. But it has two drawbacks. The first is that the This ideal interpolation is non-causal, so they cannot be used for the real-time applications, right? And the second is the impulse response is of infinite duration, so that means it will be unstable. The second type of interpolation we are going to consider is the nearest neighbor. It's the simplest method of interpolation, and it selects the nearest point of xn to approximate xrt, and it doesn't consider values of the neighboring points, as can be seen from the figure here. So this is the impulse response of the reconstruction filter. So you understand, convolving this with these samples, you get the desired reconstructed filter, right? Mathematically, we can write that HRT equals to 1 for these values, right? So that's the sampling frequency from by 2, right? Uh, sorry, sampling times by 2, right? So its width is t equals to or greater than ts by 2, right? From minus ts by 2 up to the plus ts by 2, right? Then the next category is zero order hold, right? It is also simple and practical method of reconstruction, mostly employed in the conventional analog to digital converters. It converts the discrete time signal xn to continuous time signal by holding each sample for ts, that is one sample time duration, thus yielding a piecewise constant signal as illustrated in the figure. The impulse response of reconstruction filter is a causal, right? So that's the impulse response of this uh, filter, and it has height equal to 1. So this is the mathematical description for uh, this filter. So the next category of interpolation we are considering is also called the linear interpolation. It's also known as first order hold. Mathematically, its impulse response can be described as this one. Okay, so its value is 1 minus t absolute over ts, for the t absolute is less than or equal to ts and 0 otherwise, as shown in the figure here. So that's its impulse response. Okay, so it is, although it's non-causal, but it can be converted into causal by simply delaying its response by ts seconds. The last category is the higher order interpolation. In case of higher order interpolation, they give better interpolation than the simple methods, but at the cost of higher complexity. For example, we can have a cubic spline method, and it uses special kind of piecewise polynomials function known as spline for interpolation, which results in a very accurate and smooth output. And there are various degrees of polynomials that can be employed, but the cubic polynomial is often preferred due to its simplicity and accuracy. So that's all for interpolation. The next topic we are going to consider is the discrete time processing of the continuous time signals. The block diagram for this system is shown here. So the input is continuous time signal, it is converted into discrete time, then it's processed using discrete time system, and the output of that system is again converted into continuous time system. So we can say the overall system is equivalent to a continuous time system. So the discrete time, you understand, is the signal can be obtained by sampling it. So that's what you get. And again, I think you are all familiar with these equations, right? So okay, so that's about the input, and then you process it using discrete time system, and the process signal is represented as y of n, and then you reconstruct the y of n, right, to you reconstruct the output signal using this equation, right? So I hope you understand. So to obtain the output, you have a reconstruction filter frequency response like this. So you multiply with the discrete time signal to reconstruct the continuous time signal, and it's equal to, right, and you know, because normally when you go from continuous to discrete, you have scaling factor of 1 by t. So to go from discrete to continuous, you understand we have scaling factor of t. So in this way we get the reconstructed signal. So originally your input signal was continuous time signal, right, and the output is also continuous time signal. Okay, so first you converted it into discrete time, you process it, right, and then to reconstruct the output signal, right, you should have filter having response h r j omega, and you understand simply h r j omega will should have the gain equal to t, so you cancel effects of the scaling. Now to elaborate the topic of continuous time processing using discrete time systems, let's consider that the involved system is LTI. So in that case, your output signal will be output signal from the discrete time system, right? It will be equal to input signal times the frequency response of the LTI system, right? So in that case, the output signal will be, the output reconstructed signal will be equal to HRJ omega times the frequency response of the discrete time signal system times the input signal, the discrete time signal, right? So this comes from the system for the processing, right? That is a signal you get after the processing, right, using discrete time, and that's the response of the reconstruction filter, right? So multiplying all these in the frequency domain will result into the reconstructed signal, right? So you understand h r j omega equals to this one, and the frequency response of the discrete time system is this one, and the input signal is this one, right? You understand why you are very much familiar with this one. So if the system is band limited and it satisfies the Nyquist criteria, then the output signal can be written as the reconstructed signal, right? Reconstructed signal can be written as HRJ omega. So we have the absolute of frequency if it is less than pi by t, right? Which is the Nyquist criteria, right? T is the sampling period. Okay, so if this condition is met, this we can reconstruct it only, right? So that means we can write it y r j omega equals to h effective j omega times xc j omega, which is your input signal, right? Where we defined h effective as equal to h of e j omega t for the input for the absolute frequency less than pi by t and 0 otherwise. So we can say that the overall continuous time system is equivalent to an LTI system whose effective frequency response is given by this equation, it is important to emphasize that the linear and time invariant behavior of the system shown in slide 15, right? That's continuous time processing of discrete time processing of continuous time signals. Okay, so first the discrete time system must be LTI. Second, the input signal must be band limited, right? So these are the important points so that we can have the continuous time processing of discrete time processing of continuous time signal, and it will be equal to that one. So now to summarize the topic of discrete time processing of continuous time signal, let's consider an example. For example, we have a continuous time signal and we have to low pass filter it, right? So that means we are implementing the low pass filtering using discrete time low pass filter for the continuous time case. So that's your original signal consisting of frequencies, these frequencies, and the maximum frequency is omega n, right? So once it's sampled and we get its frequency spectrum like this. So you understand all these samples are copies of the original signal at k omega s locations, right? So we have infinite copies of this one and they are all around the these are the replicas. Okay, so Fourier transform of sequence of samples will be this one. Now if you look at carefully, have you also plotted the frequency response of the low pass filter in discrete time, right? So in discrete time it has cutoff frequency equals to omega c, okay, and it has gain equal to 1. So that means all those frequencies, I think you can easily observe that these are the frequencies that are outside the pass band of this low pass filter, right? So these two corners, if you look at them more carefully, right? So after filtering, you understand in frequency domain the filtering is just the response and the signals Fourier transform are just multiplied to get the output. So that means we multiply this one with this one, so that means all those values where both are non-zero, you will get non-zero values, right? Otherwise, if any one is 0, you get 0. So that means in this band you get non-zero values. So that's what you get at the output, that is after the application of the low pass filter in discrete domain. So this is the discrete time signal you get after filtering, right? So now we have one more filter, that is the reconstruction filter, and the reconstruction filter has frequency, cutoff frequency equals to pi by t. Okay, so it has cutoff frequency from 0 up to pi by t and 0 up to minus pi by t. These values of the frequencies of the input signal, which is now y of ej omega t, will be passed, right? So that's your y of ej omega. Now this is your filter, and this filter, the reconstruction filter, it has gain equal to t. So because it's scaled by 1 by t, now it is after the product of the two, it will be the reconstruction filter has gain of t, so t will cancel with 1 by t, and that's what you get at the output. So by looking at the original signal, you can see many of the frequencies, higher frequencies, that are filtered out. Thus you have done low pass filtering using the discrete time system, right? So you have, in fact, we can say that you have ideally used low pass filter, right, for the continuous time case, right? So what you did, you just convert the input signal into the discrete time signal, right? Input signal was your continuous time signal, so you convert the continuous time signal into the discrete time signal. In discrete times, you process the uh, input signal, and after processing in discrete, using the discrete time system, you reconstructed the signal back. So it's overall equal to a continuous time LTI system, because that was continuous time input, and then you did the filtering, and again you have the output, which is again the continuous time. So I hope this gives you idea. So let's discuss it in the live session.